Perfect. Great. So, how was the midterm? What do you think? It was fair, hard, easy? What is your... Okay. Fair, hardish? Okay. Good. Fair. Work of art this time. Thanks. Okay. That's good. No problem. Okay. Okay, good. So yeah, I think it was yeah, I agree. It was better. Yeah, we did the best to yeah, to basically have a shorter exam. And yeah. Okay. Um Thank you for taking the feedback. Yeah, no, thank you for giving me the feedback. Yeah, it was very valuable to have the yeah, to do this survey before. And yeah, and we are still trying to improve things, right? I'm still sometimes going back to the presentations and see if I can explain something in a better form, or yeah, things like that. Okay, good. So today we will talk about refraction and something called depth of field. And hopefully I will show you some examples in 3 Max. So actually I need to open 3 Max. Give me a second, I will open it. Yeah. And I will also show you a couple of things on my camera, because I need to show you some lenses and things like that. So give me a second. And yeah, we are almost at the end of the term. The final exam will be harder in the sense of having more content, right? So the final exam will be basically I think it's programmed for 2.5 hours, right? So yeah, it will basically have the same style of questions, but just longer, way longer. Okay. So give me a second. I'm now checking my camera. Okay. So yeah, sorry, I had a lot of things on my computer. Okay. Good. So now let's talk about this. Yeah, the dragon is upgraded. Now the dragon has different material. Right now it seems like a glass, right? So this is exactly the topic that we will talk about, refraction. And I will yeah, basically explain the math of refraction, which is actually very simple, and how and we will see examples on 3 Max. Okay, so lettering goals for today, we will talk about refraction and depth of field, or deep of the field, sorry. Okay, so refraction. So refraction is also called transmission in some render engines. So remember, if we are talking about a computer graphics software like Maya, Blender, 3 Max, the part of the software that actually creates the renders, right? Because you're doing 3D modeling those softwares, and you also do animations and things like that, right? But when you hit render, there's another program which is basically inside that big program as Maya, Blender, or whatever, that actually performs the rendering, right? So those are called render engines, right? So for the same software as, again, Maya, Blender, or 3 Max, you can use different, a wide variety of different render engines. And it is a business, right? So it is a business too. There are companies that actually create render engines that you can use in these other softwares, right? So for example, Maya and 3 Max, the owner is Autodesk. However, if you have, for example, 3 Max, you can use the ones that are by default inside 3 Max, which are Skyline rendering, and also Arnold, which was recently acquired, and now it's basically part of 3 Max. but also you can use V-Ray or Corona or any other type of stuff. So depending on the render engine that you are using, sometimes the names of certain concepts, they change. So in certain render engines, for example, refraction is not called refraction, it's called transmission, right? Because somehow the light is basically transmitted, right? Okay, so sorry, my computer is, give me a second because I have another message here from what. Okay, no worries. Yeah. Okay, so we have something like this. We have a light source, right? And we have a light beam, right? That is basically hitting this surface. We have the normal of the surface, and we have this angle that is basically the angle of incidence from this light to the surface in particular. So let's assume for now that this object has a specific medium that is refractive. It could be glass, it could be water, or it could be any other material that is basically somehow transparent. And the thing is, the light coming from outside, coming from the air, is traveling at a certain speed. And once it basically penetrates this other material, the light will basically go slower. Okay? So that is basically what we need to simulate with refraction or transmission, right? How basically the light is reducing its speed, and because it will reduce its speed, it will basically change direction. So this is what, damn it, my computer is doing something strange. I don't know why. It's not, okay, there. There you go, okay. So basically what happens is when the light is basically entering this surface here, or is entering into this material, again, it will reduce the speed and then it will basically turn, right? So this angle will be different than this angle. Otherwise, the angle should be the same, right? But yeah, so basically, this is what happens in real life. This is a oversimplification of what is really happening, because remember, light sometimes, if we are talking about physics, light sometimes we can compute light as waves, or we can compute light as photons, and the actual behavior of light and how and why the light waves change direction when they're getting into a different material it's a lot, yeah, it's a lot more complex than this, right? But this is an oversimplification that we usually use in computer graphics, because in computer graphics, in the end, we take geometry, right? So we make geometric models that are somehow they're mimicking reality. Okay. So what we use is something called Snell's law, and Snell's law says that you have this equation, right? So these two parts of this equation are basically the same. So n2 times the sine of this angle 2 is equal to n1 times the sine of angle 1. So what is n? N is something called index of refraction, or in most softwares, they're also called IOR. So again, if you are working in Maya, Blender, or whatever software you want, they usually call IOR. So the index of refraction is defined as this tiny formula. The index of refraction is C over B. So C is basically the speed of light in vacuum, and V is the speed of light in other medium. So we call medium to basically the material in which the light is traveling. So in this case, we have two different mediums, right? We have the air and we have the glass. So the speed of light will be different on air or vacuum than on glass or diamond on other transparent material, right? So this is how we basically define the index of refraction. And the index of refraction is not something that you need to compute. There is something that you usually take from tables, right? There are tables on the internet in which you can get what is exactly the index of refraction of different materials. So you just get that number, but this is how it's basically defined. So as an example of this, in the case of glass, right, the speed of light in the vacuum, as you probably remember from high school, is 300,000 kilometers per second. However, it slows down when enters to glass, and it basically slows down to 200. Oh, I think this is incorrect. I think this is correct. Yeah, so it's basically slowed down to 200,000 kilometers per second in the case of glass, meaning that the index of refraction for glass is approximately 1.5, and in the case of air is 1.000293. We usually use 1, right? So, oh, sorry, we have questions. So Tommy, are you okay? Do you have a question, Tommy, or what is? I think we need, okay, someone is asking, I think we need to assume the density of the glass is everywhere the same. Yes, very good question. Yeah, actually, I mean, you could also modify that. That will be a super sophisticated way of creating renders, because in real life, if the material, okay, the density of a material depends on how this material was constructed, for example. So imagine that we are talking about transparent glass. There are different ways of manufacturing transparent glass. So one way, for example, is something called thermoformation, in which you have like a mold, and imagine that you have a transparent piece of glass, but like a thin transparent piece of glass. You apply heat to that piece of glass, and then you put that on top of your mold. You suck the air and basically create vacuum, and you can basically like deform the glass, or sorry, deform the plastic in the shape you want. But there's another way to create a plastic, which is using injection, for example. So you have a mold and you basically melted the glass, right? And then once the plastic is basically melted, you push the melted plastic, or the melted glass. You can also do that with glass inside the mold, right? So you basically you push the material with a lot of force, right? You're basically compressing that thing. In those cases, if you use injection, for example, and it's not done properly, you can have, in the end, you can have different density areas. So for the same object, the material could have different density areas. That is actually there are a lot of people that they use that to do research. So for example, there are some scientists that they sometimes they create like special glasses that they have different densities on the same object. I don't know if you notice that like senior or old people, sometimes they have glasses that they have like two pieces of glass in the same on the same glasses. Have you noticed that? Like basically like those type of lens of like eyeglasses is they have two different pieces of glass with different optics, and one is to basically to see the world or to see like far objects, and the other part is to see like close objects, right? So when they have, for example, when they are reading, for example, basically your eyes are going down and you're seeing, right? So if you, for example, could modify the density of a glass, you could have your glasses could basically have a different refraction, depends on the angle in which you are seeing, right? So yeah, that could also happen. That is a very sophisticated question, but in general, in computer graphics, we assume that everything has exactly the same density, unless you want to do some crazy stuff. Okay. So again, this is an example, right, with glass. So basically, the glass will have 1.5. Air has this that is almost 1. We usually use 1 for air, and for example, this is a short list for other index of refractions. So vacuum, as I said, is basically 1, air is very close to 1, and you have water, ethanol, ice, plexiglass, glass, sapphire, diamond. So as the material gets denser, right, the index of refraction is higher because it will slow, the light will be basically slower, right, when in denser materials. So in the end, this is a formula that we have, or that we need to compute this angle, right? So we have the angle of incidence, we have the normal, so we can compute obviously this value right here, right? To just take the dot product, and the value that you don't know is this one, right? So given this formula, right, we can use this. So it's basically the inverse sine, or inverse of the sine or arc sine, right, of this thing right here, and 1, which is basically the index of refraction of the first medium times the sine of the first angle divided by the index of refraction of the second medium, right? And the same happens when the light is coming out of the object, right? Because in the end, this ray of light, right, is coming in this direction, it gets bent, right? And then when it's coming out, it also will get bent, right? Because it's coming from the glass and now it's going to through the air, and yeah, it will coming out. What is interesting here is you will notice that basically this angle right here is exactly the same as the one we had here, and this angle right here is exactly the same as the angle right here, right? So yeah, that is basically an advantage. You don't need to like recompute everything when it's coming out, right? Because basically the angles will be the same. You're basically coming out from the same index of refraction and coming out to the same index from refraction that it was your outside before. The thing is, this is what, again, with what a close approximation or a close imitation of what happens in real life. And in real life, the light that is the light rays or the photons that are coming from the light are the ones that are getting inside the materials and basically refracting inside the materials. However, in computer graphics, what we do in ray tracing is we don't trace the rays that are coming from the light expecting for them to get into the camera. Remember, that is called forward ray tracing. But what we usually do is called backwards ray tracing, right? We are not throwing rays from the light getting to the camera. We are throwing rays from the camera, expecting, right, to sample the light from the environment, right? So basically, the same applies, but now thinking that instead of the ray coming from the light, this is basically the ray that is coming from the camera, right? So if we are talking about ray tracing again, this is a ray that we are throwing from the camera. So remember, there should be a image plane here, right? And it has a lot of pixels, and for every pixel I'm sending a new ray. So before talking about refractive materials, if this were not a refractive material, imagine that this is, I don't know, wood or something like that, we have this ray, we have the normal, and what we usually do is just compute the light vector and compute, for example, the Phong equation for a specular or Boolean equation. If the object is reflective, we will need to compute the reflection vector, right? And basically cast a secondary ray, and basically go and check if it hits something and take that color. So in the case of refractive materials or transparent materials, and if we want to do this with ray tracing, what we do is we get into this intersection, we have the normal, right? We have everything. And then using Snell's law, we compute a secondary refraction ray that is coming inside the object, then a third secondary refraction ray that is coming outside, and then this ray will basically try to hit something. I don't know, maybe it will hit the floor or another object or whatever, and you take the color of that new object, and that is what you get as the color of this intersection right here, right? Okay, so see, I'm reading the the chat to see if you have questions. Yeah, Raunaga was saying, oh, like bifocals. I was not, I was not remembering the name of those type of glasses, but yeah, those are called bifocals, right? Okay. So good. So if we have a different type of object, because this is a flat object, right? So the normals are basically the same. So, but we can have something like a sphere, right? So in the case of a sphere, the same will happen, right? The same refraction will happen. This is the camera. This is the image plane. We have a lot of pixels right here, right? And again, for every pixel, we just throw in a ray, right, on that direction. We'll get into this intersection, and again, because now this object is refractive, we need to compute this angle right here, right? So we use our formulas, we compute the angle, and now this is our secondary ray that is coming inside this object, right? When it's coming out, same happens, and again, remember that basically the angles are the same, right? And then the third secondary refractive ray is going in this direction right here, right? So basically, the color of this point in particular, imagine that this object is made of glass and it's totally transparent. So imagine that it has no color. I mean, my sphere is bluish, but imagine that it's not bluish, it's totally transparent. It means that the color of this specific intersection will need to be exactly the color of this guy right here, right? Because the camera ray is basically traveling along this material and bending right up to this point right here. Okay, so someone is asking, in 3D, aren't there multiple possible refractive rays? I don't understand your question. Why are you saying that is multiple possible refractive? So for this specific figure, the color. Yes, for that specific pixel in this figure, the color will be pink. Yes, it will be pink. Okay. Give me a second, because yes, we have this question, right? Someone is asking, in 3D, if there are multiple possible refractive rays. The thing is, okay. Imagine that what is happening here is, imagine that you keep the ray in the same direction, right? Imagine that you keep the ray in the same direction. So somehow what you need to do is you need to rotate your ray. Do you agree? Imagine that the ray is again in this direction. You need to rotate the ray from this direction to this direction. You see? You basically need to rotate in this direction, right? So tell me, every rotation, right, needs an axis, right? Rotations happens in an axis, which means that rotations happen in a plane. So the plane in which that rotation happens, the normal of that plane could be the dot product between this vector and the normal. Do you agree? So basically what we are seeing here in 2D, right? It also happens in 3D, because in 3D, everything is happening in a specific plane, right? So that's why it's a single ray. There are no different rays when you get this into 3D, right? Because everything is happening in a specific plane that is defined by the normal, right? And the view vector, right? Or the ray that is coming from the pixel. Okay, is that answering your question? Okay, give me a second, I'm reading the chat. Okay, someone is asking, will the angle in and the angle out will be always the same? Yes. Let me think about it. Let me think if there Okay, let me think if there are other possible options. If it's possible to not be the same, no, I don't think so. Because it depends on the density, right? And the density defines the index of refraction. So again, if you assume that the index of refraction inside the object is always the same, the angle will be always the same. The thing is, yeah, it's true. Again, it's true that in real life, sometimes the density is not exactly the same, and sometimes we want to simulate that. But I don't want to go there right now. So for now, let's just talk about this super simplified model in which the angle coming in will basically the same from the angle coming out. Okay. Give me a second. Yes, so Tommy is saying it will always the same if we assume the density of the object is same through the right. Yeah. Well, the angle of exit should stay the same regardless of the density inside the object, right? Yeah, exactly. If the density inside is exactly the same, it should be the same, right? Because remember, when you compute this coming out, right? If you're using exactly the same index of refraction for both, right? For the inside medium and the outside medium, yeah, basically the math will be exactly the same, right? Okay, someone is, if your object is like, for example, dirt sediment, the layers will have different densities. So like, I guess in that sense, very difficult to calculate. Yes, that will be very difficult to calculate. And again, if you want to simulate like super complicated materials, we will usually try to fake it somehow, right? You can modify the density of an object inside an object. You already know, we already discussed the technology that you can use. Remember that we have different types of textures, right? And between those different types of textures, we have procedural textures. And we can have 2D procedural textures or volumetric procedural textures. You remember those, right? So you can get a procedural 3D volumetric texture to define different index of refractions to different parts inside the volume of an object. That is totally possible. But again, we are talking about something super sophisticated to simulate very complex objects. But yeah, in general, objects that are refractive, usually in computer graphics, those objects are empty. I don't know how to explain this, but what I mean by empty is, imagine you have something made out of glass. We usually don't have like things inside. Whenever you need to simulate that, so imagine that you are doing, I don't know, a VFX production, and you're I don't know, you're trying to simulate, for example, I don't know, this mosquito trap in the amber from Jurassic Park, right? That amber it's a refractive material, but it's way more complicated than just a glass sphere, right? Because that amber has a lot of things inside, and sediments and bubbles and things like that, right? So solving that, creating a super complicated material, usually will just be an overkill. So what we usually do is, if you want to simulate something like that, imagine an amber piece with a mosquito inside and with a lot of like debris and things like that. Those debris and bubbles and things, right, will be 3D models inside another 3D model, and every debris and things inside the amber will have their own material, right? And yeah, basically that you will do that instead of just trying to create a super complicated material for the amber. Okay, so what happens with the rest of the rays, right? So again, this ray was coming here, was bended, right, and then bended again. It was taking this color, in this case the pink one, And remember, this is the image plane, and we are sending rays everywhere, right? So the rays are coming now on this direction. They will bend, right? Also, and when coming out, it will bend again, and now we will get this green guy right here. So what conclusion you could get given this figure right here and seeing how the light is basically behaving? What do you think the world looks when it's basically refracted by a sphere? What do you think? Inverted, flipped, upside down. Yes, exactly. That is exactly what happens with ray tracing. That is your most powerful tool to debug your ray tracing. I think last time the last time I've had this course, and we were checking the refraction part of the assignment. I think probably, I don't know, maybe between 15%, yeah, maybe between 10 and 15% of all the assignments, the refraction was not inverted. It looked kind of okay. I mean, it was deformed and everything, but it was not inverted, right? So something was wrong on the code that it was just not inverted, right? So that is the most basic thing that should happen in refraction performed with ray tracing, right? If it's in a sphere, everything needs to be inverted, right? So you can actually use that as your debugging strategy, right? Okay, so I want to show you an example of this. I want to show you the dragon because let me just come back a little bit. There are a lot of other things that we can simulate when we are doing refraction, and because again, not every object in real life, right? If we are talking about, for example, glass objects, they're not totally transparent, right? And sometimes we want to give a different look, right? So if you notice the image I have from the dragon, it's a glass dragon, but it's not totally transparent, right? It is kind of like purple. So the way we usually do that is by defining a color for my transparent object, and we basically tint the color of the ray. So remember, this ray, right, is getting into this surface, then it's get bended, right, and it's basically just traveling, right? It's traveling along this environment, looking for the color, looking for its final color. So in this case, this is basically its color. But in this case in particular, if this sphere is totally transparent, it means that the only contribution to this pixel in particular will be this pink color. You agree? However, if you want to also apply a little bit of color to this sphere right here, right, you can also get a little bit of color while traveling inside and basically combine that color with the one that you get from outside. The cool thing about something like this is that in real life, what will happen is if you have tinted glass, right, the color of the tinted glass is different depending on the depth of the shape that you are seeing, right? Or in other words, the color of the tinted glass depends on how much the light is traveling inside, right? So imagine, for example, that you have this ray right here that is traveling this enormous distance, and again, this is not a totally transparent sphere, is maybe bluish, right? It means that you could have a more contribution of this blue, right, than having a ray that is maybe just getting inside just a few inches, right, or just a few centimeters, right, and it will not have that amount of tint, right? So those type of effects are actually very easy to compute in ray tracing because you're just computing a distance, and depending on the distance that your ray is traveling, you can basically just add a certain color, right? You're basically just multiplying the color, and you can get pretty amazing results. So I will show you this. So let me open 3ds Max, and okay, and give me a second because you have questions. So refracted rays come out in the opposite direction. So if looking at the bottom of oh yeah, you were explaining yourself. Give me a sec. Let me open the scene. Give me a second. I'll open the scene here. And materials. Okay. So I will create a new material for the dragon. And remember, Arnold is a render engine, one of the render engines that you can use in 3ds Max. It's included, so you don't need to pay extra. But everything will be very similar in any other render engine. So, for example, Blender uses another render engine called Cycles. It's very good, actually, very good. And you can use V-Ray, and yeah, they are different. Okay. So I will apply this material to the dragon, and I can show you. By the way, while I'm showing you things on 3ds Max, I will not be able to see the chat. Let me check. Can I see the chat? No, I don't know why it just disappears. Okay, so I will make okay, so there's a way in which I can, if I hit render, I will have the window right here, right? And it's render and apply a totally new material to dragon, and it's totally white, right? White and open, so there's no transparency. So I can modify the render in real time, and we can see basically the if I modify things on the material, 3ds Max allows me to modify things in the material, and in real time 3ds Max will basically modify the path tracing setup, and we can see like the changes in almost real time. The thing is, I will need to decrease the size of the render, otherwise it will take a lot of time, so maybe 400. Okay, and I will decrease the number of samples. Samples is remember, if you are talking about a ray tracer or a path tracer, and in any computer graphics software, every time you see samples, there usually it's referring to number of rays, right? So for example, here total of samples or rays that are shooting per pixel is 333 to 396, and this depends on the number of samples you're taking for diffuse, specular, transmission, and whatever. Transmission is a refraction. Remember that I told you that in some computers graphic software, instead of called refraction, it's called transmission. So in this case it's called transmission, so I will just reduce the quality of this thing just to make it faster. So this is basically the render, and I can increase the size. So the quality of the render will not be like super good, but at least we can see how it behaves almost in real time. And it's taking okay. So okay, so I can show you I can create a new material. Okay, so this is a basic surface material from Arnold, right? So I'm rendering in real time here. I reduce actually the size again. I reduce again the size of the render. So now I have 350 from width, because yeah, apparently, yeah, otherwise it will basically consume a lot of memory, and I'm worried about the recording. Actually, this is not the original recording, because it turns out that yesterday when I was recording this part of the lecture, um, because yeah, the path tracing was like trying to get the image in real time, apparently Camtasia crashed and I didn't notice. So I just finished the lecture, and yeah, it was until I was basically like compiling the video and trying to upload the video to YouTube, I just realized that the last 20 something minutes was were gone basically. So this is I'm yeah, basically repeating this part of the session. Okay, so what I will do is I will get into the properties of this material. So the first thing I will do is basically get rid of the specular thing. So there will not be any reflection. The material right now is obviously um, white, right? So as I said before, what is uh, the concept of refraction in some computer graphics softwares, it's known as transmission. So the render engine that I'm using right now, it's Arnold. So in Arnold is one of those render engines in which transmission is basically refraction, right? So transmission, this number the general number from transmission is basically like a percentage, right? So if it's 0, means that 0% of the light is transmitted, or basically the object is 100% opaque, right? Or is blocking 100% of the light. So the maximum amount is basically 1. So this value can go from 0 to 1, and 1 is 100%, right? It means that 100% of the light is basically transmitted through the material. So as you can see, once I use 1, the object is already looks like glass, right? It's already transmitting everything, right? The background is white, so if I could have I don't know, maybe a texture on this on the floor, we could see some interesting patterns. But because the dragon is also like very intricate, in the end we can see like a very nice effect, right? So actually I can even modify the camera so I can make, yeah, maybe have a better look of this thing. Sec. Yeah, maybe like this, right? So we can see the dragon closer. And again, we are seeing the image right here with very low quality because I am rendering at the same time I'm recording, right? So otherwise it will be just a waste of time. Okay, so so now the transmission is 100%, right? So the thing is, this is very similar to the image from Peter Shirley's book, right? To this image, in which we can see these transparent objects that are basically refracting everything, and they're totally clear, right? So one very nice effect that I was basically telling you about is this thing of giving the glass, or giving this material, given a color, right? So we will do that. So there is a color selector here, so I can select the color, pink or purple or whatever. And for now it looks a bit weird. So the thing is, the way this thing works is it will basically tint the color, or it will apply a contribution, a certain contribution of this color into the final color, right, for those rays. Remember, in the end we are throwing rays from the camera. They're getting into this object. They're getting inside, depending on the Snell algorithm, right, depending on that formula. So depending on the index of refraction, they're basically getting inside. They're coming out, right? And they're basically looking for other surface to contribute to the color of that pixel in particular. But I can also give some color to the crystal, right? So we have this value here called depth. So what does this mean? So if I put the value, if the value is very low, it's weird, right? Because if it's 0, it doesn't look that bad, but if I increase just a little bit, it almost turned black. So depth, what is depth? Depth is it's a value that is measuring units or distance, units of distance. Sorry. So it's how much a ray needs to travel inside the object to be tinted with this color. So that's why, for example, if the value is very low, right? So if the value is, I don't know, maybe 0.02, for example, right? If the value is very low, it means that every time the ray is traveling 0.02 units inside the object will be tinted with this color. So what does mean to be tinted? Where when we are working with color values, remember that when we were checking the algorithm, for example, the Blin or Fong algorithm, the way we apply the color of our material is by multiplying, I don't know, for example, let's imagine that we are talking about the ambient color, right? So you remember that there are two ways to define the ambient color. One is if you are literally defining the ambient color as the color of your material under shadow, or the other option is to define the ambient color as the color of the ambient light. It means that you also need to add the color of the material. So in that case, you need to multiply, right, that color of the light times the color of your material. So yeah, basically contributing one color contributing to another color is just multiplying those colors. So imagine that I'm saying that every time the ray travels this distance inside the object, I will basically multiply whatever color already has, whatever color that ray already has, I will multiply by time this color. So every time I'm basically multiplying and multiplying, right, several times, I'm just making my color darker, right? Because I'm multiplying by numbers that are smaller than 0. So every time, right, the color gets more, I mean, if it's, I don't know, if this color is, for example, pink, right, it will get like a darker pink, but every time darker until it's basically black. So this is what is happening here. So if I increase this number, right, I'm starting to get a little bit of color. But what is very interesting, right, is that you will notice that the areas of this model in which the model itself is thinner, right, as these sections of the dragon here, or the teeth, or the tail. The tail is very interesting, right? So you can see, for example, here, right, this part of the tail, this part of the 3D model is very thin, right? It means that the rays are basically going into this part of the 3D model, right? They're just traveling just a tiny amount of distance, right, before coming out, right? Because the part itself is very thin. However, the entire body, right, this part of the body, this is not thin, right? It's very thick. So the rays inside are actually traveling way more distance, right? So you can see this very, very cool effect that it makes it make the glass material more realistic, right? Like a tinted glass material way more realistic, because you can see those effects. And again, this is what depth means, and you can also apply this in your code. I mean, this in particular is not listed on the on our ray tracing assignment, but you can use it, or you can also code this thing. If you do this, yeah, we could probably consider it as bonus as well. And it's not that bad, right? In the end, if you already have the code to basically compute refraction, you already have code that is basically intersecting a ray into a surface, getting, right, the refraction vector using Snell law, and basically calculating how much you need to rotate, right, and right how much the light needs to bend, or the ray needs to bend inside the object. And that object basically has an intersection when it's coming into the surface, and another intersection when it's basically coming out of the surface. You just measure the distance between those, right, those intersections, how much the ray is traveling, right, along or inside the object, and again, you can create a formula, and applying a certain number, you can apply this effect. So again, what happens if let me come back to the tail again. What happens if I increase this number, right? The crystal will be clearer, right? Way clearer every time. In a second I will get another view. Yeah, I think this one is very nice. Right, so it gets clearer because now the light or the rays, they need to travel, in this case, for example, yeah, they basically 9 units until will be basically multiplied by this color. So every time they travel 9 units, they get multiplied by this. So yeah, this is just a very nice effect I wanted to show you. And depending on the ray tracer that you're using, you can see different effects, and sometimes it's very hard to understand what are they doing, right? But once you already know how a ray tracer works and how a path tracer works, sometimes you can kind of do reverse engineering to see, oh, maybe I can achieve this with this effect, or I can achieve this with this approach, right? So yeah, so this is actually something that is very cool. This is something very cool from this render engine in particular, from Arnold, and it's actually not as difficult to achieve in terms of coding, right? Okay, so now I will change topic and I will talk about depth of field. Okay, so depth of field is an effect that happens in real life with real cameras, in which depending on the lens that you are using on that camera, and depending of certain factors from that lens, usually the aperture of that lens. Aperture is basically how much the diaphragm is open and how much light is getting into the sensor. You can see that certain objects are basically in focus and other objects are basically blurred. So if we see closer, take a look, closer look, to this render right here. And remember, this render in particular is basically what you can produce when with the first part of your ray tracing assignment. Remember, the first part of the ray tracing assignment is recreate the ray tracer from Peter Shirley. And remember, you have two options. You either follow the book and write the entire code yourself, which I personally recommend. Obviously, you will learn a lot by writing the code yourself, and mostly if you want to work in this area, you see, if eventually you want to do research, doing a master's degree, a PhD, whatever, or in general do research either in academia or any software company, and doing research related with rendering, it is really nice to have the exercise of creating your own ray tracer from scratch, right? And of course, I mean, you are obviously following a book, but you will create your own ray tracer from scratch, and you will learn a lot. But that is one option, right? The other option is that for that first part, for basically the first 50 points, again, you can do it yourself or recreate the code by yourself, or you can download the code, because the code is available, right? So you can go to Peter Shirley's GitHub, and you can get the code. Remember, we will assume that you understand the code entirely, so it doesn't matter if you wrote the code or you just get the code for that first part of your assignment. We will ask you a lot of questions about that code, and you need to understand it, right? Yeah, so you need to demonstrate the knowledge of the code. Okay, but this image is basically what you can produce with that first part, right? So the second part of your assignment is just adding stuff to that ray tracer or path tracer, right? Remember, because this project in particular is not actually a pure ray tracer, it's actually a path tracer. That's why the images look so cool. So as you can see on this image right here, there are certain spheres that are actually a certain distance that appear perfectly in focus. So this, for example, this one looks very, very in focus. This one also looks in focus. This one also looks in focus, right? However, these ones, the ones right here, they look blurred, right? These also get blurred. And you can see that it's basically there's like a fictitious plane or a certain distance from which everything is in focus, and everything that is like farther away from that distance it's getting blurred. Everything that is coming in or getting closer to the camera from that fictitious plane, it's also getting blurred. So that is what we mean by depth of field. So basically what happens in a real camera, you have the camera sensor here. So imagine that this is a very simplistic abstraction of a digital camera. And this could be a digital camera with a camera sensor, or this also could be a film camera with a film right here. And then you have the diaphragm that is it's a mechanical piece that basically allows to create like a tiny hole, right? That will allow certain amount of light coming into the sensor. And that piece of equipment, the diaphragm of your camera, it's a mechanical device that basically can change the diameter, right, of this hole, right? So if you increase the diameter, more light will come inside. If you decrease the diameter, less light will come inside. Right? Yeah, you're just blocking the amount of light that is coming inside. So imagine that this is the diaphragm where we're seeing like a cross section of the camera. And so in this case, for example, the diaphragm is very open and is basically allowing every single ray coming into the sensor. Then we have the lens. Usually the lens on cameras are way more complicated than this. They actually have different lenses, actually. It's not a single lens. So actually, yeah, probably the next lecture I will show you like real lenses. I'll show you with my camera. Yeah, but for now, imagine, again, this is an oversimplification of what a camera is. So this is a lens. It's a concave lens, and basically will concentrate the lights, the light rays that are coming in, right? They will concentrate in a single point, and it will also make the light that is coming into the light that is basically coming into the lens will converge in a very specific plane, right? And that plane is basically the focus plane. So what you can see is, again, because the way refraction works and because Snell rule works, if you trace these rays, imagine that these are light rays, right? And they're coming into the lens. And again, I'm oversimplifying the way the light is basically deformed inside. But what will happen is that coming out, they will basically be bended, right? And they will, right? Every ray that is coming in on this direction, when it's coming out from the lens, everything will be basically bent, right? With a certain angle, and everybody will converge in this specific point. So the point right here, this point in particular, is called the focus point. And this distance, right, from which the distance from this focal point and the lens is basically called the focus point. So basically everything that is exactly at this distance will be completely in focus, right? Why? Well, again, because the lights are basically converging here. So remember, when we are seeing these lights, it's like talking about samples. So you already know that if you're taking a single ray to get a sample of a specific surface, that will be incredibly precise. You will basically get that specific color, right? So imagine that these are rays. They're taking samples. If all these rays are taking samples of something that is exactly on this plane, the value for all rays will be exactly the same, right? Whatever surface you have exactly on this focus plane, if that surface is whatever is red, right? Every ray will have exactly the same value of red, right? However, right, imagine that you have another object that is not exactly on this focus plane, that is maybe here, right? You have another surface. Because you're throwing these rays and they're not converging exactly on the same position, each ray will have a different, basically a different color, right? Because they're basically sampling in different parts of the space. So that's why there's, again, depending on this angle, right? Once you're getting away from the focus plane, right? the values of these rays will start to differ from them, right? They will start to be different between them. Exactly on the same plane, all those rays, right, are sampling exactly the same color. As you are getting away from the focus plane, right? So if you are, for example, here, right, all these rays are basically touching the plane in different positions. So they are basically sampling different parts of the world, right? Physically different parts of the world. So whatever you're sampling, it will get blurred. Basically, it will get blurred. So what happens in reality is that from the focus plane, you have a certain distance farther from the camera and a certain distance closer to the camera in which objects are still pretty much in focus, okay? Because again, this is an oversimplification. This image right here is basically oversimplifying the thing. What happens in reality is that this angle is way smaller, right? So the angle in which you have the area in which objects are actually in focus is way smaller, so small that it will basically almost not perceivable. Like this tiny cone will be basically almost imperceptible if I draw it exactly with the same angles that happen in real life. So in real life, instead of seeing like a big cone here, in real life this will be almost a straight line, right? So I'm exaggerating everything here. So imagine that, right? This is a geometric exaggeration of this. So you have this certain distance from which a bit closer to the camera from the focus plane and a bit further from the camera from the focus plane, you will have things in focus. It means that every object that is farther from that area or closer to the lens, to the camera, with respect to that area, will be basically blurred. So this will be what you will obtain, right? So this guy is basically blurred, this guy is basically blurred because they are basically away from that area. So this area here, or this distance, is called field, right? So that's why, the area of focus is called field. So the depth of field is basically this distance, right? The depth of field is basically how much this area, or how big is this separation, right? And there are different ways to modify the depth of field, or modify how much farther or closer the camera starts to focus objects. So one option is to, for example, move the lens. If you move the lens, for example, away from the sensor, right? If you move the lens away from the sensor, what usually happens is that the way the rays are basically converging, right? Because you're moving, you're moving the lens. Now this angle will be reduced. And again, if this angle is reduced, basically the difference between the sample colors from each ray will be not as different, right? So if these rays are very close to each other, the difference between their sampling will not be as different. It means that they will keep everything in focus, right? So as you can see, if I move away the lens, this distance, which is the depth of field, is increased, right? Now the distance is larger. And but also the focus plane is actually moved, right? So if you move the lens, two things can happen. You can modify the depth of field, right? You can modify the distance, but you can also modify the distance of the focus plane with respect to the camera, right? This is actually what your camera does when you're basically focusing the camera. So if you have a professional camera with interchangeable glasses, for example, and you're manually focusing, right? And you're basically rotating a certain part of your lens. What is happening inside the camera, or inside the lens, is that there are certain pieces of glass that are basically coming in and coming out, right? And by doing that, you can modify the focus plane. You can either focus into a mountain that is very far, or I don't know, into a flower that is very close to you, by just moving the lens. And that will also affect the field of view. So for example, in this case, now the focus plane is here, so the objects are closer to the camera. As they are getting farther from the focus plane, they will get more blurred. So this one is, for example, this one is blurred already, but it's not as blurred as this one, and this one is not as blurred as this one because this one is farther from the focus plane, right? So focus in cameras is basically like a gradient effect, right? So as you're getting away from the focus plane, either in the direction of the camera or either away from the camera, it doesn't matter. If you're getting away from the focus plane, you will get blur more and more, okay? So that's why this guy is less blurred than this guy here. So there's another way to modify the depth of field without moving the lens. So imagine that you don't move the lens, so you are not moving the focus plane, right? So remember before the lens was here and the focus plane is exactly in the middle of the pink sphere right here. So if you keep the lens in the same place, what you can also do is to just close the diaphragm. So the diaphragm, mechanically speaking, is something like this. So as I said, it's a mechanical device. It's a piece of, right? It has like a certain amount of blades. They can have 8, 12, 16 different cameras. If they are more sophisticated, usually they have more blades. And so you have different mechanical blades that work like this, right? They're basically open or closing a tiny hole, allowing a certain amount of light that is coming into the sensor. So if you close the diaphragm, what happens is that now instead of allowing the entire set of rays coming into the camera sensor, because now I'm closing the diaphragm, right? Now I have less amount of rays. So the rays are just, I'm just allowing the rays that are basically coming only in a small portion of my lens. So because I'm allowing a smaller amount of rays, the angle from those rays with respect to the specific point in which they are converging is getting smaller, right? It means that their difference is getting smaller, so the field is basically larger. So now this guy right here is perfectly in focus, and these guys here are certain part of those are basically in focus, and then they start to get blurred as they are getting away from this depth of field. If I go further and I just close the diagram way more, right? Now I will just allow just a tiny portion of those rays. Now their angle will be very, very, very close, right? So the focus, the area of focus or depth of field will be larger, and now everything will be in focus, right? This is what happens in real cameras, and again, this is called depth of field, and this is this effect that you're seeing here in in cameras, right? So the way this is called in professional or semi-professional cameras, whatever, right? But in the lens, it's called the F. So the F is the number that tells you how much this diaphragm is open or not. So actually, if the number is very high, it means that this hole is actually very tiny. It means that the diameter is actually smaller. So for example, if the diameter is very small, we can talk about f22, f26, something like that. If you have a larger aperture, if the hole's diaphragm is actually bigger, if the aperture is actually bigger, the F number will be actually small. So for example, there are certain lenses that are very good for portrait photography. Portrait photography usually is very nice if you can have a very shallow depth of field. So you can, for example, focus the person and basically blur or defocus everything in the back. That looks actually very nice, and you achieve that by taking the photo with lenses with larger aperture. So for example, a very common portrait lens is a 50 millimeter, sorry, 1.8. So 1.8 is the maximum amount of aperture that lens can have. Lenses obviously can have a smaller aperture. So usually those type of lenses, for example, a Canon 50 millimeter 1.8 can go from 1.8, which is the largest aperture, to I think 32, f32, which is super small, right? So if you make the aperture to be, for example, 32, almost everything will be in focus, right? Because now the depth of field is very large, right? So you're getting things that are very close to the camera in focus, and also things that are very far from the camera. However, if you modify now the aperture and you make it bigger, right, the maximum amount, that could be, for example, in this case 1.8, it is very nice in terms of portraits, because like only a certain portion of what you're taking, in this case, for example, the face of your subject, will be in focus, and everything that is basically closer to the camera or farther away from the camera will be blurred. And this is something that we can achieve in rendering. It's actually look very cool. So here's an example of a picture in which I decrease the aperture of my lens. I think this one in particular I was using probably 20, no, I think more. I was thinking maybe 22. No, I think I was using probably the maximum, maybe 32. So I'm obviously focusing to very distant objects, right? So in this case in particular, I'm moving my certain amount of glasses from my lens, right, are getting farther away from the sensor. That basically moves the focus plane and also increase the depth of field. But also I am basically closing the aperture of my diaphragm. So as you can see, for example, this structure right here, it is in focus, but also these things are in focus, right? And there are hundreds of meters, right, between this structure and this structure. I don't know, maybe there's half kilometer between these two things. I'm not sure. So only the objects are very close to the camera, right? These plants right here, they're not in focus, right? But everything else is basically in focus, because the depth of field of this image is very large. I'm basically focusing everything, right? However, in this other example, I'm focusing to objects that are very close to the camera. So I'm taking flowers, for example, here. And here the depth of field is super shallow. So as you can see, in the same flower, actually, only this part of the flower is totally focused, right? So only the things that are basically on this plane right here. But the same flower, the parts of the flower that are basically going away from the camera, and the ones that are actually coming closer to the camera are already blurred, right? And of course they're not as blurred as the background. The background is super blurred because obviously it's way farther, right? So in this case, again, I'm focusing in a very I'm focusing in a specific focus plane that is very close to the camera, that is already decreasing the depth of field. But I'm also, in this case, I'm opening the aperture of my lens. So in this case, I took this photo with a 50 millimeter lens, actually with 1.8. So that is a very large aperture. I'm coming like basically everything, every light is allowed, right, to coming into the sensor, and that's why the depth of field is very shallow. So that is everything for today. So in our next lecture, we will talk about actually the solution of this. So this is what happens or this is a like a geometric explanation of what happens in the light when it's basically interacting with the lens and the camera sensor and the diaphragm, and why this effect is basically happening. And I will explain how we actually can achieve this in a path tracer, right? Geometrically speaking or mathematically speaking, what is actually the solution of this. So that will be our next lecture, and we also start to talk about accelerating techniques. Okay, so yeah, thank you, and I will see you in the next lecture.